But if that's all right, Tomislav, you can start sharing and we start with you.
Yes, of course. Hi to all. Let me just share the presentation. Okay, so I hope that you can see the presentation on your screen and in the hall. Well, I would just briefly like to introduce myself. My name is Tomislav Đurić. I come from Energy Institute Hrvoje Požar from Zagreb, Croatia. And today I'm going to present you briefly our European program, European project that is funded by I3 fund. And I'm going to briefly introduce you to the objectives of our project and our goals and mission. So let me move on to the first slide. So the project is will last for 2 years. The focus is to accelerate investment in less developed European regions. And we are going to do it through innovation, interregional cooperation. We will connect, we will identify, map, and connect local stakeholders, science, and industry. On this map that you can see that the partners who are working on this project come from mostly from this Pannonian basin. We have a lot of partners from Hungary, from Croatia, Slovenia, Italy, Belgium, Ireland, and from outermost islands, volcanic islands, from Azores and the Gran Canary Islands. So we have many excellent partners on this project, and I'm sure that there are many topics that we can share between each other in order to successfully utilize this project and to work together on the goals. So this is a map that I used from one previous European project, GEO district heating, that shows you geothermal potential of Europe. You can see that Europe has really good geothermal potential, especially this part of Europe that is located in the Pannonian Basin. The countries that are located here are Hungary and Croatia, and one part of Slovenia. Croatia especially has really good geothermal potential. But also the volcanic islands like Azores or Canary Islands or any other volcanic island has also excellent geothermal potential that can be utilized. So why geothermal? Well, it is really huge and large untapped potential. It is baseload renewable energy, unlike some other renewable energies like solar or wind. We can apply geothermal for electricity, heating, even cooling. That is especially important, maybe for the countries that have high temperatures. But also for agriculture and many other needs. The good thing about geothermal is that it has really high capacity factor, and it uses really less amount of land, a lesser amount of land in if you compare it to other renewable sources like solar. So you can see that there are many barriers to geothermal scale up. Like the biggest issue is definitely high capex, and there is some exploration risk that is present. Sometimes it can be complex to develop a project, and due to permitting and regulation, of course, there is some issues that is similar to uh, other renewable projects, like insufficient lack of qualified workforce. There is also lack of cross-sector integration, maybe the failure to recognize also cross-sectoral opportunities, low public acceptance, etc. So to conclude, there are many barriers, but the good thing is that we will try through this project to minimize those barriers. So what are the objectives of GREET GEO Project? So to encourage investment in geothermal energy, especially in less developed regions like Pannonian Basin and other European areas like volcanic islands. We will develop innovation-based value chains for geothermal projects by connecting research, industry, and local communities. Also, we will try to support the development of regional S3 strategies. Also, we are going to prepare some concrete projects for funding. We will develop some business cases, and we will provide support for applications to some European Union funds. And we will try to reduce investment risk by education and by exploring different financing models, etc. So how are we going to achieve all those goals? So firstly, we will map all the stakeholders and do the market research in order to identify potential partners for pilot projects, for investments, and for knowledge transfer. We will create a stakeholder database. Also, we will create geothermal energy strategies that are aligned with local potential and where we will identify weaknesses that are maybe present. Further on, we will have pilot projects both for shallow and for deep geothermal energy. We will also develop business cases and financing models that will be used for preparing investment for your funding applications. And there will be a lot of workshops, training opportunities, international collaboration, on-site visits, and so on. By conducting these pilot projects, those are, let's say, most important part of this project, and we will find the value chains and all stakeholders involved in some business cases. And we will foster and help the stakeholders involved to establish collaboration and to transfer knowledge and to have better opportunities to develop their project. As there are many there are many areas in the EU that have, let's say, more developed projects and more developed stories and business cases regarding geothermal energy development, like Italy. But there are some regions, less developed regions in Europe, like Croatia. I can put this map of geothermal potential of Croatia as I come from here. So we have a really huge amount of geothermal potential. But we are still not as developed as we would like to be, as we could be. But you see that we have only 13 exploitation fields, but we are heavily exploring new areas. We will utilize. The plan is to utilize geothermal energy for electricity production, for district heating. We have by now one geothermal power plant. We have several agricultural utilization, tomato production from geothermal energy, a lot of balneology, spas, etc. But we are, of course, always ready to receive new knowledge and to receive some new, let's say, ideas and ways of some innovative geothermal energy utilization. So, if you would like to participate in our project activities, in our workshops, trainings, or networking, you can scan this QR code, or you can later use this link and leave your information in our form, and we will contact you. We will put you in the mailing list, and you will be notified about our activities. That's all from me now. Thank you all for your attention, and it's good to be here today with you. Thank you.
Thank you, Tomislav. Thank you so much. We go ahead then with the presentation of the Compass project.
Everyone, first of all, I would like to thank our participants, whether it's here in Gran Canaria, but also online. We apologize for the delay to start, but we're very happy to be with you here. And I would like also to thank our collaborator here from La Palma Research Center, who are hosting us and who are part of the GREET GEO Project. So Compass and GREET GEO have been collaborating on making this event happen. And yeah, and we're very happy to be here, my colleague Dario and I, on the behalf of the Compass Consortium. So yes, of course, we started a little bit behind schedule, but we will be now presenting a little bit about Compass so that you know about the project, and then we will move to the first session on the solutions that the project have been developing over the past 3 years. We have our colleagues online that will present these solutions. Then we will move on to a panel discussion afterwards to talk about opportunities within the Canary Islands. So to contextualize a little bit why we're here as well, Compass has been working on enhancing and developing solutions for the superhot geothermal context. And we're here because we want to promote as well that development within island nations where it's always possible. And of course, the Canary Islands are relevant for that. And given also the context of the developments upcoming developments here in terms of geothermal. Really, yeah, this aligns perfectly with what we do. So, yeah, so a little bit about Compass. This is a project that started years ago, back in November 2022, with a budget of 4 million euros. It is coordinated by Power, leading geothermal company in Iceland. And yes, the ambition was to basically support the improvement of geothermal utilization by tapping into deeper, harder zones. So we're going into extreme conditions of geothermal energy. And another layer of that ambition is to improve the efficiency and also the footprint. So drilling less wells for more energy and yes, and wells that can yield 5 to 10 times more than conventional wells. Of course, there are challenges that we're trying to face, and this is why Compass exists. Given the endeavors also worldwide to push forward such efforts, the challenge and the major challenge is basically securing the wells, having wells that can withstand these conditions. So well integrity aspects are extremely important, and of course in superhot geothermal context we have high temperatures and also temperature fluctuations, but also a chemistry that does not actually help with the material resistance. So highly corrosive fluid chemistry is also one of the major challenges. So in Iceland, there is the deep drilling project, the IDDP, which is a program that's a decades-long program that has been tackling that challenge of deeper, harder geothermal drilling, and the experience with the previous 2 wells have given a lot of information. Of course, there were severe casing failures that informed basically the context regarding superhot geothermal and deep geothermal drilling. So Iceland is now preparing also for a 3rd drilling. So the IDDP3 is being planned as we speak, but we also have initiatives like the Krapla Magma Testbed, which aims to drill to magma. And here we're talking about this full spectrum of geothermal energy. So once we figure that out, and this is what we're trying to do, we can actually also not only harness more energy, but we can also create safe drilling programs for other contexts. Doesn't have to be the same extreme context, but at least having enough information and technology that can protect in case a magma pocket is hit or extreme conditions are met while drilling. So yes, so we're working on improving all these well concepts, and this is why Compass exists. Our colleagues will tell a little bit about the solutions later, but I'll give you a small overview about them. So of course, we're working on wall-casing technologies. We're working on foam cement solutions, laser cladding to tackle the corrosion challenge, and of course, like a whole comprehensive well design. So circular by design has been our flagship as well with the project to also support the cost aspect too. So thinking about the cost, drilling is costly. Engineering around geothermal is generally costly. So this is something we're trying to tackle. And we're trying to also expand the geothermal potential worldwide and having solutions that can be replicable in other places. So this is our consortium. We are a consortium of 10 partners from all around Europe. And we are supported as well by an external advisory board who has been actively involved with us over the lifetime of the project. Of course, we've been doing a lot of outreach. Part of Compass is also to support the social aspects regarding deep and superhot geothermal energy and high-enthalpy geothermal energy in general. We recently held Compass Iceland Week, where we had so a large program, including a summer school. So we're trying to train the next generation of experts in that field. We had a regional stakeholder workshop as well, same as what we're doing here. So to initiate the dialogue within Iceland about the upcoming developments and what it means to move forward with drilling in these contexts. And we've held workshops as well in Italy, where we have also our focus. So Compass focuses mainly on Iceland and Italy as case studies in a way. We also want to replicate towards island nations context and support awareness around the possibilities of these resources. So yes, we're holding right now our workshop in the Canary Islands, planning another one for the Greek Islands, and had webinars, articles, presentations, and various events. And we are looking forward to our final event in the European Geothermal Congress in October. So with no further ado, I will now give the floor to my colleagues online. So we have Tomas Macho from TWI and Gunnar Kaldal, the Iceland Geo Survey, and they will open the first session, the technologies we're developing.
Hello, you can hear me?
Yes, yes, we can hear you.
So I'm Gunnar Skúlason Kaldal. I'm a mechanical engineer at ISOR, and I will talk about a little bit about these challenges and potential solutions to the well integrity issues. So just to start, we have already a good state-of-the-art well designs for high temperature geothermal wells. That is up to a good standard and practices. However, what we are tackling is in high temperature, the casings are prone to fail. We can have failures in the casings, and the most common failures that we see are casing collapse and tensile failures of the casing. And we know that the casing problems increase with increased temperatures. Cementing issues can lead to local weak spots in the casing, and this cement quality is really important for the casing to survive. So CPL locking or cement bond locking is key for understanding the structure before it heats up. And even if the CPL looks fine, we also have seen some problems. Even though the cement seems to be perfectly fine, if there is some liquids behind the casing that can expand and create problems for us. So there is R&D work currently ongoing at ISOR and within Compass to mitigate these casing failures and increase the reliability of high temperature wells and enable drilling into superhot conditions. For example, the Krafla magma testbed project, drilling into magma, and the Iceland Deep Drilling project. Now, high temperature geothermal wells have several stages, drilling stages, and casings are needed for each stage to be able to drill safely. The casings are anchored with cement all the way to the surface. And during drilling, there's a circulation or injection of drilling fluids that keeps the well cool during the drilling project or drilling. And when the drilling has been completed and the well starts to heat up, the casings can will thermally expand, and normally they will develop stresses that are above the yield strength of the casing material. And that produces permanent deformations or plastic strains in the steel. That calls for strain-based design in the code of practice, but in most structures around the world, they are designed to be elastic. So this is quite unusual to know that we have plasticity in the structure. So the typical temperatures we're dealing with in high temperature wells are about 200 to 300 degrees, all the way up to maybe 350 in some extreme cases. But in the super hot region, we are looking into 400 to 550 degrees even. And we know if we have the current structure like it is today, then the most common casing materials will go past the yield strength at around 150 degrees to 200 degrees for K55 and 210 to 240 degrees for L80, API L80 materials. We have done a survey in 136 Icelandic high temperature wells, where 75 or 55% of them had some reported incidents. 1/4 of those of all were confirmed casing failures. And we have found that these are the most common ones, as I mentioned: casing collapse, the one on the above, and tensile failure, where the casing tears apart if it cools down after being in hot conditions. We also see that there is a high percentage of corrosion and wear problems that Tommaso will talk about solutions for after me. So yeah, this is what we are doing in Compass in terms of increasing the integrity of the wells. We're looking into the casing corrosion mitigation, cement solutions, thermal expansion mitigation, and casing collapse prevention. And I'm going to talk a little bit about these two and start by the flexible coupling. So the flexible coupling is a patented technology that has been in development at ESO since 2015. And it is based on the research that we showed you before in Iceland and around the world. And these surveys, so that we know about these problems that we need to solve somehow. We have built prototypes and tested at ambient to high temperature and pressure conditions, and there is a full casing string has been run in whole with these connections on Power's field in Nesjavellir. It was done in this year. The flexible coupling is not yet commercially available, but we are working on that. So how does it work? They allow displacement. So if you look at the graph here on the right-hand side, we might be drilling at cooled conditions, and maybe I'll see if I can. So here we start at the drilling conditions, then the well heats up, and we go past the yield strength, and it goes past it and develops permanent strains in the casing, and the well could be running here for years, and if it cools down again, then it will not go back the same route. It will develop high stresses in the tensile direction. So we could get failure like this. It depends on how high the temperature reaches and how high these strains are. So what we are doing with the flexible coupling is to try to work in the elastic range of the material. So we are not allowing the casing to get to these high stresses. How does it work? If we look into the coupling, we can see there is a thermal gap, and this thermal gap closes down when the casing expands. So instead of creating these high forces, it will allow each casing joint, about 12 meters, will allow that to expand. And if the well needs to be worked on and cooled with or injected with drilling fluids, then it simply will open up again. So this is the well that was drilled in early this year in Nesjavellir in Iceland by Iceland Drilling. This is on power and Orkuveita or Reykjavik Energy that own the well. Here are the casings that were, or some of the casing joints that were run in the well, and we have logged the well and see that the casing connection is in the open position before the well heated up. Now the well is heating up, and we are going to run logs to verify that the coupling has closed down. So we have two sizes for this. These are the main common or the most common casing sizes for high temperature wells. So 9 5/8 inch and 13 3/8 inch, and we can pretty much choose what material it's made out of, and we can select the thermal gap according to the temperature that we need. Now for the other mitigation that we are developing within Compass is this casing collapse prevention. So that is based on this, that we can get fluids trapped in the annulus between casings in the cement. And if the water or the excess water in the cement is too high, then that can develop pressures and collapse the casing. So these can be identified like this in a CPL log, where we can see that there's cement missing in a spot or a section, and so usual mitigation is to use explosives to perforate the casing at this depth. That leaves a permanent hole, as you can see here, but relieves the pressure out of the annulus. If the risk is left untreated, we will most likely get something like this, a collapse or bulge in the casing. So how can we further control this? So obviously it's not maybe the best option to have a hole in the casing. So we are trying to look into what can we do to reduce the risk. And we have been looking into the flexible cement solutions to allow some of the pressure to be relieved in the cement itself by using more flexible solutions such as foam cementing that can be more flexible than conventional cements. And it provides a pressure relief within collapsible bubbles in the cement. This is being worked on by our partners in the Compass project. And then the other solutions that we're looking into is this casing collapse protector. So the idea is simply to introduce an element into the casing wall where we allow the pressure in the annulus to escape into the well while the well is heating up. So we know that we have microannulus in the wells. We can see that from logging. With CPL loggings, after the well has heated up, we can normally see that there is this microannulus. So we are using that to actually get a route for the pressure to escape into this valve. So this is a relief valve that relieves this pressure without the casing collapsing. And this is, as I said, in development in Compass. It is at rather low technical readiness level at the moment, but we have already applied for a patent and built several prototypes that we are testing in the project. We also have looked into how to seal the element during cementing. So we have a temporary seal that is not shown here. So when the cementing is ongoing, the cement will not clog it or go into the element. So it will only activate when the well heats up. And we are testing this in a testing equipment in the Compass project, along with the flexible coupling and the foam cementing or cement that we are looking into. So this is it from me, and Tommaso, you can now take over. Thank you.
Problem. Thanks so much for the introduction. I'll begin to share my screen as well now, and we can go from there. Okay, so thank you very much, Gunnar, for the introduction and the background and some of the problems that we're having in the wells. I think is a really great solution that you guys have applied throughout the project. So I'll be talking more on corrosion and the issues that corrosion can cause within geothermal wells, and how TWI has aided the process of reducing this issue. Okay. So TWI's role in Compass is to perform and reduce the amount of corrosion on the geothermal pipeline casings. So on the right-hand side, you can see a heavily corroded geothermal pipeline casing that was in situ in Iceland. So when the geothermal fluid condensates, it becomes highly corrosive and in the form of steam and droplets. So they're forming as HCl onto the mild steel and causing mass corrosion. So within the project, it was proposed to use corrosion resistant alloys, or CRAs, and coat the internal diameter of the pipes with materials that are more corrosion resistant. So this would be stainless steel and nickel alloys. So there was a couple materials that were investigated throughout the project. So it was stainless steel 316L, Inconel 625, and Hastelloy C276 to reduce that amount of corrosion. So within the project as well, TWI wanted to perform something that was more pioneering, and that was outlined within the Compass project, that would use ELA, which is extreme high-speed laser application, rather than direct energy deposition. So doing something much faster and much more efficient with thinner layers as well, so we can be more cost-effective. So next, we just want to understand ELA. So what is ELA, or extreme high-speed laser application? So we're able to put thin, accurate layers down with low dilution and at very high speeds. So anything from 25 to 500 meters per minute. So a technology overview of ELA versus laser cladding. So laser cladding is the traditional technology on the left-hand side. You're getting a good amount of melting and heat affected zone within the substrate. But what that does, that brings the iron that might be, in this case, the iron that is in the substrate through the clad, and you will therefore have to put more layers on to get rid of that dilution of iron in the substrate through to the deposit. So you can see from the where my cursor is here, so there's around a 80-20 of dilution to substrate. So you're getting a lot of mixing, and this happens because the focus of the laser beam is melting on the substrate with the powder, whereas in ELA, the melting happens around 1 to 2 millimeters above the substrate. So what happens in this process, the melting of the powder happens above the substrate and is sprayed on. So while it's still molten, sprayed onto the substrate and sticks to the substrate, creates a metallurgical bond. So we can do high precision layers. So we can do anything from 200 to 400 micron layer thicknesses with very low heat input, anything from 5 to 20 micron heat input or heat affected zone, with a very nice surface roughness as well, and high deposition rates. So, and we're able to go at high speeds as well, like described previously, so 25 to 500 meters per minute. This is ELA in process. So just to give you an idea of the speeds that we can process at, should be another little video, and give you an idea of the schematic as well. So the nozzle is the triangular piece. That's powder's blowing through there. You can just see the powder here in this area, and the laser beams focused through the cone in the center and deposits onto the substrate. So you're able to do high speed processing. So you can see that wasn't sped up. That was in real time as well, just to give you an idea of the speed of the process. So what other applications can ELA be used for? ELA is used for chrome plating replacement. It's a thermal spray alternative, weld overlay replacement, and then application of corrosion wear like we're using within this project. And then we're looking more into a crossover with green technologies like we are currently. So there's also the use of brake discs we could use it for, and hydraulic cylinders, and corrosion resistant alloy in pipelines and valve seats. So Compass, and what Compass has done so far. So machine specification in collaboration with Horn Laser Cladding, laboratory build, recruitment of engineers, and then installation, initial design of experiments, and then the final design of experiments and some results following that. So the Compass machine was installed in September 2024. So it's been installed with a 12 kilowatt laser, so a high powered laser, a 6-axis robot that's allowed us to program in several different areas of the bed and to create the samples and geometries for the testing that we've been doing within the project. We've also installed a fully interpolated turntable that's been very useful for doing samples and geometries. And we've got a load capacity of 1,000 kg. So this is useful for the pipelines that we can add in. So this is just a feasibility study at the moment. So it's not the full length of the machine. So we're not able yet to clad the full 12 meters on this machine. We could clad 4 meters externally, and 4 to 5 meters if we rotate the component around. So, and it's just for the feasibility study, the initial feasibility study of doing the cladding within this work package. So I'll go into a little bit of the results so far and characterization that we completed on selected parameters. So not everything, these are the selected that were the most desirable, really, the best results that we got. So it's important when doing laser cladding, and especially extreme high-speed laser application, to balance the parameters right. So if you're getting too hot, something that we noticed when samples were too hot, we got hot cracking. So this is solidification cracking. When the deposited material is cooling down, we got cracking. So we don't want cracking when we're trying to reduce corrosion and a coating on components. So that's something to consider. Then also when using higher power, sometimes you might get gas pores. So the lower melting point alloys within the alloy can boil off and vaporize. So that can be an issue as well. But this sample here is most desirable, so very minimal defects. You can see there's some small defects over here, but judging by the scale bar, they're not over 5 microns in width, and then there's some tiny pores here. You can also see that the grain structure is very columnar, which is desirable for the coating compared to the substrate. And then the next few slides will demonstrate nicely the heat affected zone and the low dilution as well. So this is some EBSD completed within the component. So again, you can see the nice difference in substrate to deposit in the grain structure. So we're getting nice long columnar grains, which is desirable and expected from laser cladding as well as ELA. This is kind of what we were looking for, and we can also see that there's not much of a mixing of the material. So the heat affected zone, which is shown here, with traditional laser cladding, you'd be getting a large amount of dilution, and then you'd be getting lots of mixing here. So you'd be getting lots of iron, and then the substrate is more penetrable. This is something really nice to display the heat affected zone and the mixing that's going on, or the lack of mixing that's going on, which is again desirable for us. So we've got nickel superalloy. This is a phase distribution map. So nickel superalloy displayed in the red, and iron displayed in the blue on the substrate. So it's really doing as we expected. Minimal amount of mixing, which is what we want. So less susceptible to the HCl that would be present in some of the material. So after the analysis, we completed the analysis and we're happy. We've produced a large array of test samples to looking at the KPIs. So density, as we described, high amount of density and hardness, and then we'll go on to do the corrosion resistance and then coating thickness analysis. So coming up in the next 2 months, there's some 4-point bend test corrosion testing to take place with different stresses applied, and that'll be completed in our laboratories in Cambridge, and then also with ESOR as well, our colleagues in Iceland. And then there'll be autoclave testing, so in a brine solution or a solution similar to that of the geothermal environment, testing samples coated and uncoated, and measuring the weights of the samples afterwards to see the losses caused by the corrosive solution. Okay, right. Thank you very much for your time. I'll stop sharing.
Thank you, Tommaso. We pass now to the next presentation now, which is environmental and financial assessment of superhot geothermal resources. So here, I think he's here. Can you share? Just 1 second. Here, do you hear us?
Yeah, can you hear me?
Yes, perfect.
Okay, that's fine. That's fine. Yeah, okay, so first I'd like to share my screen. So you can see my screen.
Yes, we can.
Okay, that's fine. Okay, all right. So today I talk about environmental and financial assessment of very hot and superhot geothermal resources. So if I move on to so first we have to talk about our organizations. So I belong to TBS, so it established in 2012. So these are the core domains of the TBS, and we are located in Manchester, UK, in the very heart of the city, near to the University of Manchester and you know that MRI. And we have 30 plus European Union and EQRI projects, and also we have a 150 plus partners, and we have 4 spin-off companies, more than 12 years of experience, and we have 70 plus. So these are the criteria of our organization. Just I would like to opportunity to tell you about this one. So if I move on to the next slide, this is all about what I talk about today is about the cost and environmental assessment tool what we developed in Compass projects. So these are the contents I'm talking about. So you can hear me appropriately?
I'm sorry, the slides are not passing.
Slides? Okay.
Yes, so we just see the first slide and this.
Okay, slides are not passing. Okay, I'm just going to the. If I move on. If you could share again.
Okay. And the whole screen, I think that would
so
be easy.
the slide changes in my desktop, but Okay, I will share it again. Should I share it again? Okay. And then see what happens.
Sí, creo que debería haber sido.
Yeah, share it again. I'm not quite sure what's. Okay, just me. Share it again. Okay. Just one.
Para tener acceso.
Screen one. So can you see my screen right now?
So you can see the screen. Yes, now it's correct.
So if I move the slide, can you see the changes?
Now it's changing.
No, it's changing. Okay, okay. So these are the contents of the talk today. So first I would like to, so what are the rule? Yeah, so you can see my third slide or fourth slide right now. So
Yes,
yeah, here I just what are the rules in Compass projects? So what we are doing in the Compass projects, we are developing two estimator, one what we call the cost estimator, another we call it is an environmental impact estimator based on the LCA model for environmental estimator and also parametric cost model. Yeah.
Sorry, could you put it in presentation mode?
Presentation mode. Okay, right, that's fine. You can see my presentation mode right now. There's a whole. I don't know. So can you see the screen changes?
Yeah, but we're seeing it in the presenters mode. So if you have two screens, you should need to pass it to the other screen.
Okay, just a minute.
So I don't know, can you go to display settings, which you have on top of the screen?
So if I move the slide, so can you? I'm not quite
If
sure.
you go to the top of the slides, it says show taskbar and display settings.
So your voice is breaking down. I can't understand exactly what you're talking about. What I understand, if I changes the slide, so you can.
So hi, can you hear me?
Yeah,
This is
now.
Al. So if you go to the top left of the screen and you click on display setting and you
Top left
switch.
of the display setting. Yeah, I can go to the display setting and
then,
swap presenter view or slideshow or duplicate slideshow.
Exactly.
Which one?
The first one, the swap.
First one. Yeah. So now you can see my introduction.
That works. Thank you. Hi.
Yeah. So it's worked properly now.
Yeah. Thank you.
Okay, right. So where actually, so I just talk about what are the rules in Compass projects. So what we are developing, what we're doing in the Compass projects, we are developing two models. One, what we call the cradle to grave LCA model for the surface plants and the well completion, and also we develop parametric cost model for the surface plant and for the well completions. So how we do this one, and that's why I'm just trying to be explaining. And based on these models, we also constructed a estimator, the Compass cost estimator for surface plant and also Compass environmental impact estimator for surface plant, right? And in addition to these two tools, we also developed cost and environmental performance modules for well completions based on the LCA model, cradle to gate LCA model, and the parametric cost model for well completions, using some Compass technology components, casing and cementing materials, and other technology components. So the functional unit of the well completion is the 1 meter of drilling activities, and I'll talk about only the cost estimator for surface plant and the Compass environmental impact estimator for the surface plant. If I move on to the next slide, so this is the functionalities of the cost estimator. I'm just telling you what we do with the cost estimator. It can estimate the LCOE of the existing plants or the future proposed plants utilizing superhot georesources. And also not only calculating the LCOE, we also can evaluate the other financial parameters such as NPV, payback period, and IRR, and return of investment. So, and also we can analyze the results, the sensitivity analysis of various financial parameters such as NPV and others against the discount rate and revenue factor, changing the discount rate and revenue factor or annual cash flow increase or decrease. So we can see how the changes will occur due to the change of the revenue factor and other factors. And the functionalities of the environmental impact estimator for surface plants, we can estimate the total resource consumption because we are doing the cradle to grave. So we need to know the detail, that inventory data of the plants in construction, operation, and maintenance phase and the end of life phases. And then based on this data inventory, and we can evaluate the environmental impacts of these plants in 3 phases in terms of a functional unit, what we call electrical energy produced per, what are the environmental impacts per megawatt hour of electrical energy production by these plants. And also we can representing the results graphically in the tool, what we have developed, that environmental impact estimator. If I move on to the next, these are the model what we have developed for the cost estimator, what we call the parametric cost model for surface plants, mainly based on the GTM, and also that model can allow us to estimating capex, opex, and other cost components. And based on this one, we can evaluate the LCOE, and also we can estimate the other financial parameters. So these are the method for the LCA model for surface plants. So we choose cradle to grave. That's why we are considering the construction phase to end of life phase. And we, for modeling of the geothermal power plant, we need to know the basic data inventory of this existing plant or the proposed plant. And also for the case study, we considered the two perspective. One is the Icelandic and the Italian perspective. That's why we are choosing two plants, one from Iceland, another from Italian. They are using the very hot georesources. So we collected all the data, inventory data from these plants, and converting all this reference flow data into a resource consumption data and then functional flow data, and use this functional flow data using our CIMA-Pro LCA tool. And this CIMA-Pro LCA tool will be linked through API with our environmental impact estimator that can estimate the environmental impact, such as climate change, carbon footprint and other environmental footprints. So these are the method we are following for LCA. And these are the just snapshot for that cost estimator tool for surface plant. If I go into the tool directly, I hope so I can move. If I'm not, yeah. So you can see my desktop where I just go into the home page of the that cost and environmental impact estimator. Can you see my screen?
Yes, we can.
Okay, that's fine. These are the home page, right, where we have developed 2 cost estimator tool, one for the well compression, another for the surface plant, another 2 environmental impact estimator, another for the well compression, another for the surface plant. And where we have just mentioned, we first estimate the total resource consumption in 3 different phases, and then converting all these resource consumption data into a functional flow data, and then we can evaluate the environmental impact in terms of a 1 megawatt hour of electrical energy production by the plant. So these are the way. So it takes time to be, if I go through all these components. That's why I'm just going back to this one. There's some snapshot. There's a time constraint. That's why these are the tool where we can choose the plant, which plant we are evaluating the cost analysis or cost performance for the plant. So I'm choosing Icelandic plant, and then what are the characteristics, what are the temperatures, what are the resource depth. These are the necessary parameters data we need to be evaluated. If I go to the next stage, then we have a lots of parameters we have to be entries, the some cost parameters, fixed charge rate and blah blah. So if I move on to this one, these are the just glimpse of the understand. So how we more than 100 data we need to be put into this one. So most of the data are default parameter from the GTM, and some of the data from the what we have from the secondary literature for the Icelandic case study. So this is where I can evaluate. So once we choose this one, then we can click the analyze cost performance, and then it can evaluate the LCOE. So how much LCOE for that particular plant, what we are choosing, either Icelandic plant or Italian plant or our proposed compass plant. So that can evaluate the LCOE values. I can just show in a one table, and other cost values. So for example, capital cost, how many million power per megawatt hour, or what are the exploration cost, and what are the total annual and operating costs. This is that all the things can be evaluated from the cost estimator tool. And then also it can evaluate the other financial parameters, NPV, PBP, IRR, and ROI. I'm just showing the results here. And also it can compute the sensitivity analysis for the net present value against the discount rate, or net present value against the cash flow. So these are the way we can just understand what are the functionalities of the cost estimator for surface plants. If I talk about now for the next 5 minutes about the environmental impact estimator for the surface plants, then you can go to the tool again, and then I can go straight away this site. So you can choose which plant you are considering. So here we collected all the data for the Icelandic plant, Hellishide, and the Italian plant, what we call backnode plants, right? And also we are collecting all the data for the proposed compass plant as Icelandic perspective and the Icelandic. So which plant we are considering? If I'm considering only Icelandic plant Hellishide and the compass plant as Icelandic perspective, and these are the parameters what we have. And based on this one, we can calculate this one. If I go back to the presentation slide, then yeah. So yeah, so there's some slides. So these are the necessary data you need to be put into the environmental impact estimator tool to be evaluate the environmental impact of the selected geothermal power plant. And if I move on to the next slide, these are the resource consumption data on in the construction phase. You can see this one. So this is the screenshot from that tool, what I'm just showing here. This is the maintenance phase data, atmospheric phase data, and end of life phase data. And also all this resource consumption data can be converted into a functional flow data. That's why we can say that our environmental impacts in terms of a functional unit of what we call here, it is a 1 megawatt hour of electrical energy productions. And if I move on to the next slide, and these are the results what we are presenting for the Italian plant and for the compass plant as Italian perspective. I can show what are the carbon footprint. What I mean that climate change is about 50.8 kilograms CO2 equivalent per megawatt hour of electrical energy, and for the compass plant, which is about 9.87 kilograms CO2, what we have evaluated from the data we have. Right. So if we have a more primary data, that result can vary. So this tool can just demonstrate what data from the secondary literature we have for the backnode plants. We have evaluated what are the environmental or carbon footprint of this plant, and also in the compass plant in Italian perspective, we can generate the result. Then we can realize that we can understand that what are the impact of the compass plant as Icelandic Italian perspective or Icelandic perspective. So these are the environmental footprint results in a glimpse, and also in some graphical presentations. And finally, I just concluded what we have developed for the cost estimator, and what are the benefits from these two tools, right? So we can compute key financial parameters, that LCOE and others, and also helps to invest decision making. And also sensitivity, we can do some sensitivity analysis. We can also understand which will incur the more cost, or evaluating the multiple cost scenarios for better planning and decision mapping. So these are the benefits we can have from the cost estimator for the geothermal projects, utilizing very hot or super hot georesources. And if I move on to the last slide, I think, yeah, so these are the benefits from the environmental impact estimator. We can evaluate the environmental performance of the geothermal plants, supporting sustainability goals. We can understand and understand the what are the risks, or right, and also regulatory compliance with the environmental standards, what we have got the results, and what are the environmental standards for the geothermal sector, and also improving our decision mapping and transparency and stakeholder communication. So finally, these two tools and also other two tools for well completions will be integrated with the Compass decision support system developed by Sintef, and that works seamlessly within the Compass DSS. They are developing this Compass DSS, and this Compass DSS can be enhances the geothermal project's feasibility studies, right, for utilizing very hot georesources. That's all from my side. Thank you very much.
Thank you so much. Yeah.
Okay.
I believe we pass now to the next section, which is engaging communities in deep geothermal development.
I'm just stop sharing. Okay, thank you.
Thank you.
Thank you.
Okay. Hello, everyone. Hello, everyone. I'm Dario Bonciani. I work for the Consortium for the Development of Geothermal Areas, which is a public company based in Italy to scan geothermal territories. And we are a partner of the Compass project and work on social aspects and communication of geothermal energy to the local communities and citizens and non-technical audience. Okay, so let's start. In our presentation, we did this presentation with Amel, which is working with me on these aspects, and we will report the results of our research and some proposals about how to manage the public acceptance of local communities towards deep geothermal projects. So, in general, as we all know in this room, geothermal energy is a renewable and local energy source. It can contribute to support the energy transition, and it has several properties that are valued, can be that distinguish this energy source with to other renewables. So it can be.
The online participants are not
Okay.
sure. I think that is correct.
Okay, so yeah. Geothermal energy can be used as a baseload energy, but it can be used also as a flexible energy source. So it can support the development of other renewables, because it can provide heat, cooling, and power, and it can provide energy when the other renewables are not available. So it's a different renewable energy source. In addition, it can provide cooling and power for space heating and cooling and heating for space heating and cooling, and for industrial processes and production processes. But its development faces challenges that are not just technical challenges, but also non-technical aspects like the social resistance. The social resistance, most of the time, the social resistance is linked to a lack of awareness on technologies, poor or not clear communication about the opportunities offered by geothermal energy, and the lack of awareness and communication about the potential risk of geothermal developments, and the lack of engagement of local communities in geothermal projects. Because if we, as we will see later, if we don't involve local communities in geothermal projects, then there is a wide distance between the operators and projects and the local communities, and this can result in problems under the acceptance point of view of local communities. So the consequences, the social acceptance, the social aspects should not be underestimated, because the local action groups and the network of action groups against geothermal energy can influence politics. So the influences can be the delay of or stopping of geothermal projects, reaction of the request for authorization, and even a damage to the entire sector, because the echoes of contestations can reach the governments and even the European Parliament. As you can see in the triangle there, the society, industry, and governance are closely linked, because the oppositions are listened by politicians, and of course the industry, the geothermal development can have an impact on this society. So all these three elements are closely linked. There are many factors that influence the social acceptance, and there are, in general, there are no standards to be applied to deal with social acceptance issues, because there are differences between one place and other in terms of local and social, in terms of socioeconomic conditions, culture, language, and then geothermal energy is a complex matter, because for example, photovoltaics and wind, we can feel the wind, we can see the sun, but we cannot see the geothermal fluids. We cannot see the underground, the reservoir wind. So it's a difficult matter to explain geothermal energy, maybe more than other renewable energy sources. Okay, but in the last time, the public developers, operators, and authorities are putting efforts to prevent contestations and find the ways to go ahead with project developments, because contestations, many times contestations can block and stop geothermal projects. Okay, within the Compass project with Georg, with Amel, we did research on case studies on how the social acceptance has been managed in different countries. We took into account more than 40 publications, case studies in 9 European countries, more 4 non-European countries, and we saw how we saw how the public acceptance was managed, and we were able to distinguish between best practices and bad practices according to the results of the activities that were carried out at local level with the communities. So there are positive examples, like in terms of communications, negative examples, and the same in terms of for the social engagement. Because it's important to communicate to the local communities and to engage with them, as I was saying in the first slide. So the communication should start in the early project development. It should be tailored. Communication of risk and mitigation, the risk and mitigations measures should be communicated, and local authorities and scientists should be involved. And we should clearly explain the benefits, because it's a negative example is to create, for example, too high expectations or to communicate benefits only, because there are some case studies where high expectations were created, and then the local communities were expecting too much and more than what the project could offer in terms of socio-economical benefits or direct uses or access to energy, for example, in remote areas. Then it's important also to engage with local communities. The engagement should be tailored to the local context. And it's important to start the engagement and the communication in the early stages of the project development, in order to prevent voices among the local communities and fake news, for example. And citizens should be involved in the decision-making process, because it's a bad example is to have a top-down approach, so to impose a project at local level. And another bad example is to have closed doors events without involving citizens and local communities. The results of our research allowed us to elaborate recommendations on how to address the social aspects of geothermal projects. So there are more steps. We identified more steps. The first is before the project, the exploration. The exploration should be, the studies should not be just on the geothermal resource, but they should concern also the local context, the local culture, the socio-economic culture aspects. And it's important also to identify potential allies to be engaged, during the project development. In the second step, during the explorations, it's important to start liaising with the local community, the local authorities, start the communication on the risk and opportunities for territories about geothermal energy, and the mitigations of potential risk related to the project development. And it's important to start to have meetings with local communities to listen their concerns, but also their proposals and their expectations on geothermal energy, start a sort of dialogue with them to agree on the mitigations, for example, on the landscape, on the impact on the landscape, and mitigation and opportunities in terms of benefits so financial benefits for territories, but also direct uses of geothermal energy for space heating and cooling or for production processes. Then it's important to, before the exploitation, the submission of the exploitation permit, is important also to involve citizens in the co-design project, so in the decision-making process related to the development of the plant. Of course, it's not necessary to involve people in the choosing of the right turbine or technical topics, but it's important to involve them, for example, in decision making of the landscape aspects, and to involve them on how to develop the geothermal project, the development phases, and so on. And yeah, and then after the exploitation permits, it's important to communicate, so to allow also communities to visit the construction site, and to allow them to touch with their hand the geothermal project. Within the Compass project, we are carrying out survey and activities at local level in Italy, in geothermal territories. So we elected 4 municipalities in one of the 2 geothermal territories in Tuscany, in the southern part of Tuscany. As you can see the bottom of the page. Yeah, it's a remote area with natural areas, with parks, natural reserves. And we decided to do the activities there because there is the renewal of the geothermal lease from the regional government in these days, in these months. So there is a quite animated debate on these aspects. And then because the acceptance in that area is not very high. So there are committees, I guess, geothermal energy that are that are protesting, I guess, the development of new plants. So we started with a communication campaign on geothermal energy. We opened a Facebook web page. We have a page on Facebook to circulate news on geothermal energy. We started a survey on the perception of geothermal energy, involving the representatives of the civil society and local community. And we did an engagement workshop with local communities to inform them on geothermal technologies and to engage with the public to understand their views and proposals on geothermal projects. The engagement workshop was held at the end of last month. The results of the survey report that in terms of development of new plants, most of people answered that they agree on further development of geothermal plants. About the involvement, the direct involvement of geothermal of local communities, many people answered that they don't agree. They prefer that the local administrators should liaise with the operator instead of local communities. But in any case, the majority of the interviewed people answered that it's better to involve local communities in the decision-making process related to development of geothermal projects. Then about the concerns and the arguments on geothermal energy, related to geothermal energy, and the development of new plants. most of attention is on the environmental impacts and impacts on the landscape, and concerns in terms of impacts on health for local communities. So these are the main aspects on which we should put more efforts in terms of communication. And then, of course, people would like to know more also about the potential benefits of geothermal energy. The results of the participatory session, there were some proposals that are in line with the results of the survey. The survey is still ongoing. So about 3 topics: mitigation of impacts on the landscape, benefits, and communication engagement of local communities. The proposals of people were that it's important to develop green barriers in geothermal plants, and for example in pipelines in the countryside. All the plants installed in that area are using the flash technology, so they are big plants. The benefits, they propose to reduce cost for heating and cooling, for power production, for the fees for the power, for the use of electricity for local communities. More services, because they expect an increase of people after as a result of the increase of job local level. It's in the countryside, and that area is affected by the population, because it's in a remote area, and resources for. They propose to use the resources, the financial resources coming from the royalties, to use them in different activities, including cultural events. In terms of communication, seminars, people proposed also education in schools, because this is important it's important to communicate and to teach what is geothermal energy to the young people and to kids and can report what is geothermal energy to their parents. So this is important, and at least they can trigger curiosity between their parents, and then the engagement for design, to have the proposal to have open meetings, and also involve institutions, and not direct. Some of them answered that it's better to have an engagement through the institutions and not a direct engagement of local community. This is all for the research that we conducted in part of the work package related to the social acceptance. I give the floor to Ahmed.
Thank you, Dario. And we've seen examples of projects that failed because of the social challenges and resistance from communities. They've had everything ready. They were, they had the legal license, the financial license, and they proceeded. But because there was a gap between the community and the development, there were issues, and several projects were halted. And this is why there is a need for social license to operate. So for geothermal, a social license to operate would look like reducing risk of public criticism and conflicts, providing basically this framework of operation in terms of the connection and dialogue between the developer and the communities. And this is also an ethical tool to ensure transparency, to reduce the investment risk, and also to just have a more versatile and easier engagement for financial license. And this is a work that we have developed years back, not too long ago, within another project called Geothermal. And there we designed a model for the social license to operate, conceptual model for it. So this model is based on the pyramid model, and to be able to measure where we stand in terms of the social acceptance. So to dissect it a little bit, these are 4 blocks that you see. So you have on the left side the different levels of the social license, from withdrawn to acceptance, approval, and co-ownership, which is the highest. And then you have the different barriers, indicators, and solutions that are related to each level, or related with the values level as well, and the stakeholders. So it is important, if we talk about stakeholders, to know who are stakeholders within each project. And it's what we have is that we have 2 levels of stakeholders. We have the core stakeholders, our local communities, our local authorities, local organizations, NGOs, and researchers and users that are directly affected by the development of the project. And then we have the broader stakeholders, which are at governance level, and so on. And Díaz explained it a little bit, that the effects can go from top down, but also from bottom top, and these stakeholders can influence each other in terms of the acceptance. So going back to the levels, when we have a withheld or withdrawn social license, what does it look like? So usually have fundamental conflicts in values, shutdowns, blockages, sometimes like sabotage and violence, and also rise boycott. And this means that basically we're not legitimate to proceed with the project. So this is the first barrier, and legitimacy is the first normative barrier. And here, what is needed is basically sitting on tables of negotiation and reaching out to politics and discussing how can those conflicts and values be overcome. And then once we are past that, then we have the acceptance. And acceptance is a bit of a vague term, because we talk about social acceptance generally, but this is a very vague term. Here, it only means tolerance. The project is at the tolerance level, and so there are still lingering issues. There are threats, sometimes watchful monitoring by NGOs, and presence of those NGOs around. And here, what it means is that the credibility is not yet shown, or so the developer is not credible in the eyes of the communities. And here, there is importance to just have dialogue, sit around dialogue tables, and dialogue can happen in different ways. There are many ways to go about this, and you're showing that the developer knows what they're doing, that the environmental issues are tackled, there is experience, etc., etc. And once we're past that, then we are in the approval place in terms of the SLO. And here, the developer is seen as a good neighbor. There's a pride in collaborative achievement. So if there's success, everybody feels as part of that. And so this is the positive mid-ground. But we're still not yet there, because the ultimate barrier is trust. And trust is hard to gain, very easily also lost, and hard to also retrieve. But when it is there, then the communities feel that they co-own the project, that they are also part of that they are in this co-creation as well. And this happens through the co-production and and participatory aspects around the development in general. And here, when we are there, the co-ownership, this is also called psychological identification. So people identify with the project or with the resource. Sometimes if we talk about the industry as a whole, for example, in the case of Iceland, people identify with the resource because geothermal has shaped the culture. The cultural fabric within Iceland is shaped by geothermal. So a geothermal project is seen as a normal energy project, which is very telling. So here there's political support, a united front against critics, so communities can actually stand by the developer in that sense. There's advocacy, there's co-management as well, and I mentioned details about that earlier. So in terms of value levels, of course, it correlates. The lower the social acceptance, the lower the mutual benefits. And mutual benefits are keywords in terms of geothermal projects. This is about the nature of the resource itself. So it is a domestic resource. It is developed and consumed locally. So benefiting both parties, like in terms of communities and the developer, is extremely important. So once we tap into that, we can increase those levels of acceptance, and here, like where we can reach psychological identification of co-ownership once we are at the highest levels of mutual benefit. And this goes with community engagement and activities around participation, decision making, talking at schools, educating, awareness, and so on. So this is what the SLO model looks for, geothermal energy, and some copies as well here, so you can grab them if you want. So this is the model that helps navigate the social aspects around geothermal development. And here I'm going to give an example of Iceland again. So through voting, Iceland has managed to integrate basically geothermal energy, and initially it was for the district heating, and back in the 60s, the Geothermal Fund was established by the government, and now it's called the National Energy Fund, and this is support from the government that allowed for this initial push. So giving loans to people who wanted to develop geothermal energy, and then for projects that succeeded, they could pay back those loans. For the ones who didn't, they only paid help, and this is a kind of an incentive as well from the governance level to push for that. And we're seeing that as well now in the Canary Islands with the developments that are coming up. Like having that support from the authorities is extremely important, and but also like having people saying yes to that. And this is the story here. And Iceland is now a pioneer in the use of geothermal energy, and the Reykjavik district heating is now considered among the largest in the world, with 75 million cubic meters a year of hot water, and it actually serves 2/3 of the population of the island, which is amazing. So, yeah, the factors that need to be considered are mutual benefits. We need to benefit from that resource too, and the social license is intrinsically linked to the legal license and to the financial license. It can affect them directly if it's not there. It's an ethical tool, so everything that has to do with also the CSR and the core values of the developer are important. Yeah, and I'm going to give another example, and this time is from Spain. And this is an example that a case study actually that we've had within the Geothermal project of housing cooperatives at the heart of Madrid. So people wanted to shift to geothermal. The heating in Spain is supported by gas, it's extremely expensive. So these communities wanted to change that, and they opted for geothermal, and they actually co-funded that project themselves. They got involved themselves in switching to green energy, so geothermal. We've had 2 housing cooperatives that use heat and cooling from geothermal, and there were no geothermal social acceptance issues because the people or the end users were themselves the developers. And they also involved people that they could trust, experts that they trusted to do that. And there was a full community alignment. So there were cooperative members, architects, engineers, main contractors, and maintenance companies. There was open communication between them, and there was an influence in the decision making. This led to a very successful, actually, end result, because they even got the prize of the best geothermal installation within Madrid. It inspired other people to do the same, and this is the effect of actually showing that it's doable. So pilot projects are extremely important. Once successful, you show that the resource is safe, it is feasible, you can do it, then other people start doing it, and then it creates possibilities and opportunities to grow. So this is the second example. So yeah, the social potential of geothermal energy is extremely important. It can change the economy of many places, cities, countries. And here, yeah, showing a little bit about the value chain. So creating jobs, all sorts of jobs are needed in this value chain within the geothermal development, and at different levels, different levels of development, different types of expertise. We have like legislation and planning, the infrastructure, investment and feasibility, financing, etc., until the decommissioning. It is possible to create a whole ecosystem around this, and it can change curricula as well, like having professionals sometimes like directly trained to integrate that workforce, or transitioning from other workforces like the oil and gas, or other types of renewables, like trying other types, like the integrating the communities within from those other renewable energy communities. So it is quite considerable when we see the full picture. And another example here is cascading effect of geothermal development. So here it is the example of the resource park in Reykjavik in Iceland. And here we talk about like power plant and what you could create around it. And it is very, very famous that you heard about the Blue Lagoon in Iceland. So the Blue Lagoon is a direct effect of that development. It's even more famous than the development itself, but it is a place that could attract a lot of tourism for Iceland. A lot of tourists actually stop by Iceland and go to the Blue Lagoon to just see the Blue Lagoon, and then continue their trips. And this tells a lot about this possibilities of actually feeding like other sectors in the economy, and not only because that resource park could actually attract businesses around also by products of geothermal, which are CO2 and in general, and it could create basically a sustainable research and development infrastructure, production, business. So yeah, Spark was pioneering in creating value from the various geothermal resource streams that would have gone to waste otherwise. But it's like once you tap into that potential, it is possible to create and co-create. Yeah, so this is another successful example around another type of development, electricity generation. Yeah, so the social license to operate model has been relayed as well within the latest report of the World Bank on the socioeconomic benefits of geothermal energy. You can also check it there, and I'm gonna give here just some highlights and conclusions around this. So building trust and credibility is important with the stakeholders, and the SLO is not a means to an end. It is an ethical tool, so it has to create a relationship between the developer, the community, and the stakeholders. Generally, it is important to sustain that relationship, to nurture it, to create transparency around the activities, and by participation, and yeah. to the decision-making process. And yes, efforts to gain the SLO start prior to the implementation of the project. This is often a mistake that a lot of developers do. They're busy like getting the permits and the funds to funding to actually move forward with the project, which is also like a great effort because geothermal developments are difficult to actually finance. The investments are not easy to gain, but this does not mean that the social aspects need to last or only when something comes up, which is often the case. So the efforts start prior, they're continuous in time and proactive. A lack of withdrawal of the SLO can put in jeopardy a project, despite the presence of the legal requirements, financial licenses, and a strong SLO can help obtain actually financial license. And this is the case of the cooperative in Madrid. They could actually unlock that financial license for themselves through wanting and desiring the industry to be there. And some conclusions generally about what we presented today with Dario. So social acceptance of deep geothermal projects is shaped by specific project context, how risks and benefits are communicated, and the degree of community engagement. A transparent, continuous, and tailored communication is essential, not only to inform, but to build lasting trust and credibility with stakeholders. Engagement must begin early on and go beyond consultation, involving local communities meaningfully in decision-making. Force tangible, context-sensitive benefits, especially those that support local livelihoods or services, and strengthen the community alignment and ownership. And there's no one-size-fits-all approach. So engagement strategies must reflect local conditions, values, and history. And last but not least, the social license to operate. It is a dynamic, non-formal agreement that complements legal and financial licenses. It helps reduce risk, improve project viability, and ensure geothermal development is more inclusive and more resilient. So with that, I thank you very much for your attention, and I think we got the Q&A session for the audience here, but also the audience.
From the online audience, we did have a question before, but it's not related to this. People will have access to the presentations after the workshop. I have also been asked by people.
Yes, yes.
So we will send the presentations to everyone, both in person and online. Do you have any more questions?
Scientific, okay. So I can be somewhere in order to test how society refuse this. So you have been talking about the danger, for example, about landscape problems. We need basically injuries. And I truly think that one of the most important problems here is the similarity or the use of drilling in order to get the geothermal energy. So drilling in Spain means petrol or fracking. Okay, so fracking has caused a lot of problems in England, and I think that the best way to communicate there's no problems at all is focused. Is fact. But according to all these presentations, I have not a real image of where the danger is indeed, okay, because it's renewable energy, and you have drilling pipes and things like that. We have seen problems about the corrosion and the mechanical problems with the machinery, but when you put stage problems, human health, for example, I don't see that, okay, but I don't know. So it will be something about this. And not only landscape, but for example, the problems about does it produce in the future earthquakes, because this is a volcanic really big island. And this is a problem because we have recently problems with level and so this is important. So how will you approach these specific problems here? And where is the problem and where not? It's I suppose just a scientific point of view, and that for me that solves it. Okay, you have a reputation as a science point of view. It means nothing. I mean, don't take it, okay? But anyway, we did that, I think.
Yeah, I think this touches the identity itself of geothermal. Because geothermal energy, when we speak about it, is different technology depending on the contact, depending on the wanted utilization, and so on. So yes, really, it's a bit really important to acknowledge that we drill for oil and gas, of course, we also drill for water, and it's vital. So it is also a way to access. And the underground, that we mentioned it earlier, it is abstract because we can't see it, but most of it from the underground, and it's important to have awareness around that. And geothermal energy has its specific operation system depending on the type of development. The means that takes that heat, because we want to access heat and transform it. It is water or steam, then it is transported, then it is transformed in case of electricity production, for example, and there's an infrastructure around it. And most of the infrastructure actually, yes, of course, you have the surface infrastructure, but you also have the underground one. And it's important to understand the geology, like of the area, to be able to do it safely, but also the sustainable development of needed to to have that balance. With each resource development, there is a risk. So geothermal energy has its own set of risks that are communicated, they are known, but are important to communicate to the communities in order for them to understand what is going on. In the volcanic islands context, of course, people live with the resource. It is there under their feet. Sometimes they see it on the surface. I mean, with the geothermal fields, you can see the steam around. You can see the alteration and so on. So it is just a matter of connecting the dots and of communicating when there will be like a development somewhere to be able to communicate what this entails. It's also with drilling, there's the noise pollution. You can also smell a little bit of sulfur, but it is in terms of landscape visualization as well, to be able to have an infrastructure that is not affecting the tourism potential of the area. So this is an aspect that is not very pushed forward. Like in the case I always like give the example of Iceland. For me, this is how you do it best from an aesthetic perspective. Like when you visit the power plants, when you go and see the development, it is nicely done. Like it's not ugly to the eye. So people like go, and there are like exhibitions and tourism. Like tourists go to visit these power plants and installations. So the aesthetic aspect is more important than many would think, and we have those discussions within Compact, but also generally within the community. We need to have art involved also in that, and design, like really comprehensive design thinking approach to be able to have those successful installations happening. So it's a multifold work in terms of, depending on the context, the risks are communicated, and identified. So yeah, I don't know if I answered your question, but this is just to give you a little bit of the picture.
I think all the geological aspects and all the technical aspects, including the potential risk and the mitigation measures, should be appropriately communicated to local communities, to people, without sending too easy messages. So, yeah, this is it's quite challenging. It's not easy, but I think, but it's the key to go ahead and to develop projects in this period, this age. We have social media, we have fast communication medias. So yeah, so it's important, and it's important. Well, depends on the characteristics of the communities, but it's important to involve in this framework. It's important to involve technicians and scientists, for example, researchers from public institutions, public bodies, that can be seen as a third party, because there are the open and the local communities, their scientists, sometimes they are annoying. But there should be also a third party that can be represented by a public research institution that can communicate the potential risk, the results of their studies on environmental impacts and impacts on health, potential impacts on geothermal energy. I think, yeah, and the mitigation measure. I think the geothermal energy, the geothermal development is an industrial activity, so it should be seen as it is. But it can provide benefits for communities and for the society in general, because it's a clean energy, can produce energy as a base load, it can provide heating and cooling. So,
And these are steps like in terms of also regulating the development, because the environmental impact assessment is an integral part of that development. So there are environmental studies to actually assess the risks and provide solutions, how to mitigate those risks and so on. So this is related also to the regulations around the environment and environmental impact. So, yeah, I hope we answered your question. Do you have any other question? Us or our colleagues as well who have been presenting earlier? Questions from our online audience? Otherwise, I think we are ready for a short coffee break, and then we'll resume for the panel discussion. Thank you very much.
Just in case of any that, so it will be another point to take into account, because it's normally when I see this type of companies from Iceland, from Australia, from the United States, for example, your projects are, according to the presentation, outside. That means like that. That's maybe you can approach people just in terms of, okay, we are going to comply with all the rules that it will be minimum.
I think you mentioned like a very important point to see that it works. And this is where engage stakeholders, especially and just to see maybe other countries are doing other areas. It's possible that it can happen in similar geological context and get inspired, because it is so abstract that many they push it because it is too complicated to deal with. More projects are complicated by nature, but still they're doable. And when they see that it also affects positively the economy, the livelihoods of the people, I think it makes a shift. And then they shift from thinking only about solar and wind, which are extremely competitive because they have time developing and also like the deployment. It's just very high speed, but geothermal is a stable resource. So I think it makes a difference to engage visibly and delegation, exchanging, and so on.
Here in the Canary Islands, we have even documentaries about the projects that are being developed in other countries. This gives like an approximation the things that can be happens here, but people know really good the other technologies, like for example the PV, even people installing the house, but for example they don't know about the geothermal, even for the low temperature. And here in the Canary Islands, we have like 14 facilities that have low temperature geothermal systems, mainly in Lanzarote, and sometimes some of them in Tenerife, Gran Canaria, but they don't know that we are using these resources. And this is something that would help, because they know, okay, we are using, but at different level. It's the same technology, but with other
applications.
Yeah.
I think the Mendel diagram is the reference, when you show it and you show the thermometer, and then you have different temperatures and different applications at each level. It's very visualization, just being able to see it. And read it is extremely.
Yeah, this aspect. Do you have any plan to use directly geothermal heat, for example, for cooling, desalination, or interesting topic for islands, but also for production processes, agriculture sectors, including both heating and cooling, because most of people don't know that it's possible to generate cool with the heat from the underground. So this is a quite interesting part of the geothermal sector. So are there any plan or studies to use directly the heat?
But in my opinion, for the desalination, I think that is not the best alternative, because here we use the reverse osmosis that have energy consumption of around 2 kilowatts hour per cubic meter. It's really efficient, and we have a lot of systems that could be a good option for some kind of application. We have a system like that, but using the heat that is produced by the conventional the thermal generation. Okay. But the system don't work. Yeah. And the osmosis, reverse osmosis, was just the solution that was selected. It is Canary Island maybe is the place, Spain, of course, that have more facilities like that because we don't have enough water for us in a systems quality in the terrain. I mean, it's more the salination is the key. For the agriculture, I think that is not also. I think that is not a good option because the temperature here is quite stable. For example, the tomatoes that you saw before, it's only with a greenhouse, it's enough. However, we have other applications, like for example, the turrets. You can use the heat for the swimming pools, for example, or even you can use for laundries. I mean, it's just to adapt to the kind of heat that we have. Not and some people that come outside also ask about this kind of application, the desalination and the use of for agriculture. I think that is not the best alternative. Anyway, I don't know because the technology is quite different. Maybe someone said, okay, I think that could be a good alternative because I'm going to start this system.
Yeah.
Where is geothermal needed and where it can absolutely. And this makes the difference when trying to pitch it, like to know where it's.
You know, the largest opportunity here in the Canary Islands is to decarbonize the electrical production. That's the main goal. But like I said, when you it's a journey. You know, it's not a one project off, but it's a journey because you know if you can decarbonize or make a project that is successful, then you'll have many byproducts. And you know when you know what the byproducts are, then you can fit some kind of industrial or something to it. Just like we've done in Iceland. You know, first we started just producing hot water, then we started producing electricity. And now we have these geothermal parks where we have all range of industrial. So that's the opportunities they will show when you're already installed it, and then you can pick types of industrial to that or some production session and so on. It's not very good to define that in the beginning of the project because then you're not managing expectations very well. It's good to.
Yeah, that's what I was reporting also in my presentation because if you keep too high expectations, for example, you say, yes, we are increasing the production of from heat geothermal heat here to produce tomatoes. So that makes sense.
It makes sense.
And this is another question on not on direct uses, but on the different uses of geothermal fluids. What about the use of minerals, elements, the geothermal fluids? Do you have any data, information on possible uses of, for example, it's a topic of trend now is lithium, but it's not just lithium. For example, there are projects to extract silica from geothermal fluids. You have one example in Iceland, and there are examples in Turkey. Is there any knowledge about the possibility to extract minerals?
So no, we are not. I can't say that we have information on that. You can elaborate on that, but we have had that will probably show up any real research wells, but we don't have information on that. But there will be possibilities in regarding that. But what specifically we cannot.
Yes. Tomislav.
Yes, thank you. Thank you very much. Yeah, I have a question actually for one gentleman from the audience. I tried to hear, but I couldn't hear as loudly. It's difficult. But one gentleman mentioned that several buildings are using the shallow geothermal, or was it shallow geothermal or some other way of geothermal for heating and cooling? If I heard well. No.
I will like hearing you very flat. So can you repeat the question?
Yes. So one gentleman from the audience was talking about that several buildings in Gran Canaria, in Lanzarote, and other places are using geothermal energy for their purposes, for heating or cooling. I didn't hear quite good, so if maybe can you elaborate it a bit?
Yeah, that would be like Santiago.
Yeah. Yes, here in the Canary Islands, we have like 40 facilities in which they use the geothermal energy for heat applications, mainly in swimming pools, also in hotels. There is a company, this island especially, that have the knowledge and have been installed these systems since, what, I don't know, even 1990. It's a solution that have been tested. For example, in the Insular Authority of Lanzarote, they have a system. I had the possibility to visit another one in a hotel that is just in the south region of Lanzarote, in which I could see the system. It's a good alternative because we have a very high potential, mainly for the hydrological basin that we have in the island. Okay, because there we have water and water with heat for the temperature of the system. So it's a good solution in some cases. In other ones are not a good solution and have been tested, but not with the good results. So yes, here we have for the audience. If you enter in a web page that is called Observatorio Energético de Canarias, OECAN, I'm going to right now here, you can download a strategy that was developed by the government of the Canary Islands, which they define the potential that we have from the low temperature, low enthalpy geothermal, and also the high enthalpy geothermal. And there we also have the different facilities that was recognized in this analysis.
Excellent. Yeah, I didn't know that you utilize shallow geothermal as well. We can describe it as shallow geothermal, right?
Sorry.
Can you repeat again?
We can describe this technology that you mentioned as shallow geothermal. Is it shallow depth?
Yes, it's less than 200 meters of deep in this case.
Yes.
But they have it's an open system, okay? That means that you have a drill to collect the heat and another one to return. Yeah, this one.
Yeah, I know. Okay, thank you very much. Thank you. If you can just send me that link, and maybe Ariadna, if you can connect me later with this gentleman, I would like to have maybe some kind of connection.
Yes, okay.
Thank you. And I have another question for Mr. From the Reykjavik Reykjavik Geothermal, regarding the depth of planned wells, and as well as the prices of well drilling. So, what are the planned depths? Is it medium depth or higher? Do you have any geological data in this moment, or are you still in early phase of exploration?
So we have acquired or measurements and acquired geological data, but that for the wells will be between 2,500 meters, 3,000 meters. That and the cost, I guess it's like how to calculate it from dollars to it's like probably 5 million euros per well. It's a rough estimate. Don't have the exact number. Really positive. Yeah. 5 million euros.
5 million, and if I heard well, 2,000 meter well, right?
Yeah, it's really be accessing for more than 2,000 meters. Be close to 2,500 meters.
And drilling rigs are going to be imported from some other region, or are they locally present?
No, we don't have any local drilling companies. Maybe that's also a part. We don't have that many drilling companies in the world that are familiar drilling with geothermal wells. You can count them on both hands or even one hand. So we want to go with a drilling company that we were familiar with and we sure that have the knowledge.
Okay, yeah. Well, we have in Croatia, we have let's say an issue with high drilling price because of the really big interest now, and a lot of activities are going on now currently. So the prices are really high for the drilling rigs. And the waiting list is also pretty long. So, but yeah, this is also one of the issues that we are trying to encounter with and try to solve them. But yeah, that is always an issue. Drilling price is we know that it can be lower, but there has to be a good market for the drilling companies and some competition and so on.
Yeah, that is something that we see, especially in Europe, for the last 2 or 3 years, because there has been very much or very high demand for geothermal drilling, and like I said, there are not that many companies that are specialized in that, but the prices have gone. Yeah, they have been going up and are going up. So because that's it's a limited resource, these drill contractors, at least here in Europe. So we see the prices go up.
Yes, but I'm keen on finding why do you think that there are not many companies that are capable of drilling geothermal wells?
Yeah, so
it is. Yeah.
Let me elaborate that, because we are talking about drilling in high enthalpy geothermal. So the temperatures that we are expecting are in that range. That are not that many companies in the world that have been doing drilling like this. The most experienced drilling contractor in this is from Iceland. So yeah, but there are a few others, but there are not that many drill companies that have been drilling in high altitude fields, in Europe. So because we don't have that lots of them in Europe. We have them in the US and other places in the world, but most of the high-enthalpy fields are in Iceland. So if you just count Europe, then so that's a problem that we see.
I think that narrows down the choice, but also the reliability of the having experienced pillars to deal with extreme contact is extremely important as well. And I think this brings up a layer of also capacity building, because there's less and less people who are actually enrolling in drilling programs and drilling engineering university level. So this is actually a call to push for that and promote drilling, because it's not only for oil and gas. Geothermal need that, and it's important to promote. So this is a very good segue actually to the last question, and it's related to the superhot geothermal. So are we able to think about it in this context? Of course, I mean, high-enthalpy context that the Canary Islands have, then there's potential for it, but we're able to feel ourselves in terms of what if the should be.
Yeah, of course, we should think about it and think about the next step. And this is something that we've been thinking about in Iceland for decades, but we haven't been successful in making this step, but we're trying. And I think that, we should always, that would be the ultimate goal, to get there and get the technology and the experience and everything to access superhot geothermal and how to utilize it and harness this extensively, because it's a great potential if it can be harnessed. And I'm quite sure when we will get it. Don't know when, but we will get it, because what we've seen through the decades in Iceland, we have had so many problems to solve, but they have most of them have been solved along through this journey we had by Iceland. The sulfur gas problem that has been solved, like Hellisey power plant, it's carbon free today. So, like I say, you take the step, you take one step, you have problems coming up, but they get solved a little bit later. So I think, superhot geothermal, we are getting there, and I would say within a decade we will be pretty close to harnessing it. We just have to continue this journey.
Nice. I'm curious about permitting and association processes. How long does it take in Iceland to get the authorization for geothermal power plant on average, like an estimation?
Okay, so that's a very good question. If I could tell you exact number of how long it takes, that would be nice, but I can't. So we have, in Iceland, we are already, the framework isn't that clear. So there has been, for the last decade, it hasn't been, going quite smoothly, but I would say if everything goes well, it would be like 3 years.
3 years.
Yeah. And then that's, that's getting all the permits, everything, finalized. So for that, in that, we also include the research drilling. So I would say, you would take 3 years from you have, made some research until you can start working or drilling for the power plant, not the research roads. So
that's probably currently they take 3 years.
Yeah.
What about the beginning? At the beginning, you started building power plants, geothermal power plants. How did it take the permitting at the beginning? Because I can understand that it has been like a learning process on the way, and it has taken, every time it takes less and less time, because the technicians that analyze the projects, they have a better knowledge. But at the beginning, like I would suppose they would take take longer?
I'm not sure that the answer that I'm going to tell you is going to help you because I think, you know, in the beginning we didn't have the framework or the regulatory. So I think the first one we built took lot less time because you didn't have, you know, this framework that you had to go to and take all the steps. And yeah, but that's like 40, 50, you know, 60 years ago. But we have been trying in the last year, you know, to simplify the regulatory work and, you know, what governments, you know, has, you know, intervention with so on and so on. But you know, the legislation, I think that's the largest problem because we have this framework for all energy or energy project, and that's something that is to difference in politics.
Since you're working now in Tenerife and Palmas, what will be your expectation? Like, because we're involved, a lot of people here are involved in normal photovoltaics and wind projects. We know how long it takes to get the authorization processes for these kind of projects. Geothermal is complete. So I'm quite curious, like I have hard for me to make an estimation. So I don't know if you have like a...
So the plans that we have, it's like it's 4 or 5 years, then we would have pilot projects running.
Okay, so 4 or 5 years.
Yeah, 5 years, yeah.
For the complete permitting.
Yeah. And to have the, you know, small scale power plant operational.
And are you gonna try to get like, because there's no, as long as I know, there's no framework for the administration process. Do you know if there's gonna be like, or from your side and this side, are you like pushing that? Get like a framework or the...
So we have, you know, we have the local in Tenerife, we have the local government with us, so we are trying. We're not gonna push it, but we're trying to, you know, keep the timeline like we set it up. But that's a really big, you know, I wouldn't say an issue, but you know, uncertainty factor in the timeline that we're making, and that's, I would say that's everywhere in also Iceland. So that's, you know, in these geothermal or energy projects, the framework for legislation and everything, and that's the most uncertainty that you have in this project. Because you know how long it takes to drill, you know how long lead time is on a turbine, and et cetera, but you know how the framework will you know actually work. That's why we have the local people, companies with us and the governments, because this is something that we don't know, how it will turn out. But hopefully it will turn out well. At least it's going quite well, so that's really good.
If you have any statements to close it, have a discussion with. It's been really good to have a discussion with you. And
thank you for the quite interesting perspectives for the development of geothermal energy in Canary Islands. I see also, according to the questions from the public, strong interest, which is I believe it's very important to develop geothermal energy systems for both for power production, heating and cooling, and to support the other renewable. completely phase out from fossil fuels that can support the development of all the renewables when, for example, when in 2029, geothermal energy can do this job.
Not one solution, only one solution. Yeah, a combination of solutions that can fill the gap. And we are very excited about the future developments and the upcoming drilling in Canary Islands. That's a successful unfolding. Thank you again. Even work on panelists, work our audience here, and the audience online, and we will be sharing the presentations in the next stage, and we look forward to continuing the discussion. And so,
Thank you very much.
Thank you also, Dario and Ahmed, for coming here to the Canary Islands with the Compass project. And I do just remind everyone, if you want anyone's contact from any of the presenters today, also let us know and we will make sure to get you in contact with them to try and advance these kinds of projects. And also, whoever wants, we have the lunch outside.
Thank you to Arianna for the efforts for the Palmas Research Center staff, because without them, this event was not possible.